Yeah, good afternoon, everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Yeah, today we're talking about design of FIR filter, finite impulse response as a class of linear time invariant filters. So, in this case, the transfer function of the filter uh, is but it is followed by h of z, where h of z is equal to y of z by x of z. So it's also equal to summation k equal to 0 to capital M into pk z power minus k. That is same that coefficient by 1 plus the summation k equal to 1 to capital N ak z power minus k. Yeah, here finite impulse response FIR filters, if order of the that n is equal to 0, no feedback. This is the main motto using this particular concept. So let us consider an FIR finite impulse response filter of length. Length, it is specified that what you call capital M. So or we can consider that where order of the filter capital M, capital N is equal to the taper M minus 1. So watch out, this order are number of delays. So the time if we are considering the finite impulse response filter of length M, so that are it is all are depending upon n order of the filter n is equal to n minus 1. Yeah, that time we know that output response, so that y of n is equal to the summation k equal to 0 to m minus 1, the coefficient bk into x of n minus k, which is also equal to what you call the summation k equal to 0 to n minus 1 h of k into x of n minus k. So within this, where x of n is the input, realized thing, where x of n 2 up to what you call that y of n, to use that to delay value, but like this, that y of n, x of n versus x of y of n will be so like this graphically. Can immediately obtain the impulse response with so in terms of the x of n, where x of n, we know that where x of n is equal to delta of n, that I got the impulse response, where that impulse response h of n is equal to y of n, it is also equal to the summation k equal to 0 to m minus 1 bk into delta of n minus k, it is also equal to b of n. Yeah, the impulse response is of finite length capital M as required. So note that finite non-recursive filter like finite impulse response filters have only zeros, no poles. That is, it is specified. Only zeros, there is no poles. Hence, known also as all pole filters. Okay, so that means that non-recursive filter is nothing but what we call finite impulse response filters, also known as feed forward. We can consider that feed forward or maybe non-recursive. Feed forward, or than the name that non-recursive, or we can consider that transversal. Transversal. This is the concept related what we call FIR, finite impulse response filters, also known as feed forward or non-recursive or transversal. So within this, distal FIR filters cannot be derived from the analog filters. But in distal filter, by using that what you call IARE filter, so already we have derived something. But here, this case, distal finite impulse response filter cannot be derived from analog filters. So rational analog filters cannot have an finite impulse responses. So why bother that while we are not using this filter cannot be derived from analog filters? So we have to use, we have to collect these all points. They are inherently stable. So they can be desired to have a linear phase. Okay, This is the way. So there is a great flexibility in shaping their magnitude. The magnitude response will be expected your desirable thing. They are easy and convenient to the implement. Okay, remember very fast implementation using fast Fourier transform. Okay, so using this, the digital filters cannot be derived from analog filters. So that means that a rational analog filter cannot have a finite impulse response. Apart from this, we have to consider this all 4 points. They are inherently stable. They can be designed to have a linear phase. There is a great flexible in the shaping, the magnitude response. They are easy and convenient to implement. They are by using what you call either maybe DFT or FFT, but it is specified that very fast implementation using the FFT is the suitable. So how it is suitable for that? After implementing this design of FIR filter, maybe by using windowing techniques, or maybe using the Kaiser, or maybe what do you call Hanning or Hamming, or sometimes what do you call Blackman window, and so on. So after that, we can use the remaining exchange and so on. Okay. Due to this FIR filter, so we know that FIR finite impulse response filter, that output response is equal to y of n. It is followed by where y of n is equal to the summation k equal to 0 to m minus 1 h of k into x of n minus k. But here we know that all where h of n we know, and x of n is also we know. These two are the finite duration sequences. Their h of n and x of n, their convolution is also finite duration. The duration of the sequence where the output y of n is that y of n is, it is specified if it is what you call the duration of the sequence y of n, it is specified what you call L plus capital M minus 1. Okay, let us consider that n, we are having the tall condition n greater than or equal to L plus M minus 1. Let us pad the sequence h of n and x of n. It is specified that x of n and h of n. Okay, so with zeros to increase their length to capital N, and perform the n-point DFT, the frequency domain equivalent to that y of k, where y of k is equal to h of k into x of k. Okay, by using this all analysis of a filter with the y of n and the y of k, after applying the frequency domain, before that finite duration sequences with what you call x of n and h of n and x of n, you note that n-point DFT y of k and then n-point IDFT y of n, so can be used to compute the standard convolution product and thus to perform using this all where y of n is equal to the summation k equal to 0 to m minus 1 h of k into x of n minus k. You have to consider that all if it is n, what happens that where n less than or equal to L plus m minus 1, what happens? Yeah, if it is specified where capital N greater than or equal to L plus m minus 1. Okay, like this. So we have to interpret this mathematically, and which time it is the paired sequences h of n, x of n with 0 to increase their length to capital N and perform the n-point discrete Fourier transform. After that, we will expect that all frequency domain equivalent is where y of k is equal to h of k into x of k. Yeah, FIR design methods. Of course, we are having a lot of so many methods are there. With reference to that, here we have to concentrate on FIR design methods. Impulse response truncation. So the simplest design method has undesirable frequency domain characteristics. Not very useful, but introduced to that. So windowing design method. So one is it is based on impulse response truncation. Other one is windowing design. That windowing design method simple and convenient but not optimal. But our expectation is optimal. Okay, so we require that optimal thing by using this different algorithms like what do you call approximation. Sometimes we have to consider Savishu approximation and yeah, enclave and PC enclave and so on. Okay, but the windowing design method simple and convenient but not optimal. But by using the optimal, we have to use the different methodology or algorithms. That is order achieved is not possible. That's why so that windowing design methods it is very simple and convenient but not optimal. So you go on searching that are optimal things. You have to digging that different algorithms like Remage and PC and Crow and so on. Okay. So optimal filter design methods. That method series is followed by what you call. We can consider back to our ideal low pass filter example. We have to consider. So like this, it is. So what it is? Let us consider, for example, simple ideal low pass filter defined the desirable frequency. Desired SD of omega is equal to 1 if mod omega less than omega c. 0 if omega c less than mod omega less pi. It can be shown easily that the impulse response is given by SD of n. Okay, that SD of n is omega c by pi into sin omega c into t c n by omega c n. Here also go on substituting this all n value. If it is that when n value is substituted where n is equal to initially 0, 1, 2 and so on according to our specification. Okay, so here desired impulse response has a sync shape, yeah, which is non-causal and infinite duration. That is a clearly this area somewhat clearly cannot be implemented in practice. So by using this all mathematical notation, by writing this piece of code, using the MATLAB, using the built-in or inbuilt functions, you will expect this type of responses. Impulse response has a sync shape which is non-causal and infinite duration. Okay, so with this, that h of n infinite in duration, to compute any sample of the output, we need to know all samples of the input both in the past and in the future according to what we call symmetric and anti-symmetric. Maybe non-recursive filter. We know that non-recursive filter concept unacceptable. So what we just clip off the sink at some large n, the 10 values. The 10 value it is impulse response maybe h of n, or we can have that h cap of n. Okay, it is also equal to what you call sine of n omega c by n. Okay, so for this case, for n value, if it is magnitude n, that is not it is specified that n is equal to 0, 1, 2 and so on, but it will not be negative values. Okay, for that case it is using that mod n less than equal to m and 0 otherwise. Here the what the frequency response now the response looks like a omega c. That omega c is this value is it is specified where omega c is equal to, we have to use initially maybe 0.1 or 0.2 or 0.4 in terms of that pi, and the different values of M, capital M. So one observation: ripples in both passband and stopband transition not abrupt, okay, changes leading to the transition band. Like that, right, to verify that the frequency response now looking like a, for omega c is equal to 0.4. So this is the effect of the different values of capital M. Yeah, there is approximated filter obtained by a truncation. Here there is a truncation here. If M is equal to M, it is specified that M is equal to 15. How it is truncated? The transition band with normalized frequency versus h&d power j omega. So go on, increase that M value. M value is equal to 30, where M value is equal to 200, and M value is equal to 1000. Go on up to this. So there is the dot. This transition band gets narrowed as M tends to infinity. The ripple remains. Maybe they maybe increase or decrease. So somewhat it is truncation or maybe without truncation. These are all approximated filters obtained by truncation. Okay. So with this, now coming to this windowing design methods to expect, we will expect some what we call without error. But without error, other option is it should be output response should be optimum. Yeah, to be expected. Truncation is just pre-multiplication by a rectangular window. We know that it is defined that a rectangular window W of n omega n is equal to 1 if n is substituted, where n is equal to, n is equal to 0, 1, 2, 3 and so on, capital M minus 1. Yeah, that omega n is equal to 0 otherwise. This is not very clever. Obviously one introduced the delay. Yeah, if it is, we are substituting that either n is equal to 0, 3 or 4 or m minus 1. So apply this Fourier transform, h of omega of the truncated filter, that impulse response will be appeared, where impulse response h of n is equal to the desired of sd of n into w of omega of n. So h of omega will be appeared. Okay, that h of omega 1 by 2 pi integral minus infinity to minus pi to plus pi, sd of lambda into that window. It is specified a particular window of into omega minus lambda into d lambda after applying this Fourier transform. Okay, so where w of omega is the Fourier transform of the rectangular window. It is specified that particular window. Okay, it is rectangular window. Now it is defined that window w of omega e power minus j omega m minus 1 by 2 sine omega into capital M by 4 by sine omega by 2. Like this, the Fourier transform of the rectangular window, they are right to define. It is followed by w of omega. Yeah, rectangular window frequency response. How they are calculating the frequency response? So the Fourier transform of the rectangular window, just we have verified, w of omega. It is followed by as per your truncation effect or after applying the Fourier transform of the rectangular window. Admits at the magnitude and phase responses. Okay, what do you call? So that particular window mod w of omega sine omega into m by 2 by, so mod sine omega by 2, where that omega less than or equal to pi. Get an angle theta of omega. So like this we have to measure using this our mathematical notation, and sine omega m by 2, it is specified that m value m by, if it is that m is 10, if it is m is equal to 10 or 7 or whatever it is, it will affect that all what you call theta of omega as well as what you call mod what you call W of omega. Okay, it will affect this and this theta of omega. Okay, so that is the W of omega as a piecewise linear phase. Piecewise linear phase will observed in particularly graphically. So practically, mm, one uses truncated and delayed impulse responses. It is followed by h cap of n is equal to h cap of n minus capital M minus 1 by 2. Where we know that h cap of n is nothing but this value omega by pi into sine omega c by omega cn into 1. We have to substitute that r minus m minus 1 by 2 m minus 1 by minus m by minus here it is specified minus m minus 1 by 2 and so on. Okay, yeah, minus what do you call that, plus m minus 1 by 2 into n, where capital M is the filter length and where n is, we know that out of the filter it is specified that n is equal to m minus 1, is known as, it is the filter order of the filter. Okay, so delay, you have to observe that delaying operation, that it introduces linear phase term. It is the resulting filter is causal and has the linear phase. It is non-causal, it is non-linear phase. So like this. So the magnitude of rectangular window frequency is like this. If it is rectangular window, that m is here, m is specified. M is specified, that is 16. Based on that, what the width of the main lobe and side lobes, peak of the side lobes, easily can observe that one. This is the magnitude of the rectangular window frequency response. Okay, so we have to verify in practically. Width of the main lobe is increases, whatever side lobes which after that, easily can estimate the solve magnitude of the rectangular window frequency response. Of that we can decide the factor. Okay, like truncated filter. The truncated filter, it is the what you call desired frequency response, is d e power j theta. So that window, this is the desired frequency response here. This is the desired, but is d of e power j omega. After applying this windowing, where we will expect that all what we call w e power j omega. Okay, so now here it is truncated. The higher the area under the side lobes and the larger the impulse in the pass band and the stop band. Okay, so you can observe that using the solver for identifying the higher the area under the side lobes, larger the ripples in the what you call pass band and the stop band. So we can consider in terms of the filter, it is the truncated filter. Okay, like this, the width of the transition region between here when desired and using the windowing effect, region between the pass band and the stop band in the HD of omega, it increases with the width of the main lobe of W of that window base. Okay, like this will verify that all responses omega versus that SD e power j omega. This is the ideal requirement. Ideal, we would like to have where m is small, we computations, it is specified the capital M. That if you are using the windows like a rectangular, Kaiser or Hanning windows, the W of omega close to a delta direct mass for H of omega to be close to the desirable frequency SD of omega. So that SD of omega is defined is equal to 1 if mod omega less than omega c, 0 if omega C less than or equal to mod omega less than pi, like this. This is the ideal low pass filter SD of omega. These two requirements are conflicting. So it is a conflicting based on the ideal requirements. Based on this all requirement, we can change that according to m value is on increasing, or if it is decreasing, or the time ideal we would like to have m and that window w of omega close to what you call h of omega to be close to sd of omega. Like that, based on these ideal requirements, we will observe the things. Now we are verifying the increasing the dimensions of the window. Okay, that window that where m is equal to, it is specified that width of the main lobe either decrease or increase and so on. The time, if m is specified, where initially that m is equal to 10, here where m is equal to 30, where m is equal to 50, where m is equal to 80. So the time is you can estimate the normalized frequency versus normalized amplitude. Okay. Due to this, the width of the main lobe decreases as m is increases. If it is m is the m value is increases. Okay. The main lobes will be decreases like this. Go on increasing the m value 10, 30, 50, and 80, and so on. Okay. So based on this, the area under the side lobes remain constant as m increases. Go on. This is one aspect. The other one is where m is go on increasing that m value, the area under the side lobes remain is constant as the side lobes are constants, like here. The side lobes are constants. Okay, here the side lobes, if m is increasing, the side lobes are okay. The side lobes remaining constant as m increases. It is increasing the dimensions of the window. Okay, like this, we will interpret this one. There is a conflicting ideal requirements. The width of the transition region between the passband and the stopband and h of omega increases with the width of the main lobe of w of what you call w of omega. Ripple in the passband and stopband is dependent on the area and the side lobes. Yeah, for consider the rectangular window or other windows of it is conflict the ideal requirements. So for the rectangular window, the width of the main lobe is increases as this is the main lobe. Okay, that main lobes are increases as capital M is decreases. Okay, but it can show that the area under the side lobes remain constant as per these previous results. Okay, transition region gets smaller, but the ripple remains. The problem is sharp discontinuity of the rectangular window. This is the big problem. How to overcome this all by varying that all m is decreasing or m is increasing or decreasing certain period, somewhat it is discontinuity of the rectangular window will not be sharp. Yeah, sometimes the sharp discontinuity of the rectangular window. This is the big problem. How to overcome these all problems? Go on increasing the m value and main lobes, how it is varies, how it is interpreted. If it is main lobes are increases, that m value is also increases the time. What are the sharp discontinuities? Other option is if main lobes are decreases, the m value either increase or decrease is connected to the sharp discontinuity of the given window. It is specific the rectangular window. And to overcome this problem, problem is identified with reference to that reflecting the ideal requirements. Okay. Yeah, solutions to sharp the discontinuities of rectangular window. Problem is identified. How we are solving this problem? Within this, use the windows with no abrupt discontinuity in their time domain response. These are the way for solving this previous problem, and consequently low side lobes in their frequency response. This is, okay, next we have in this case the reduced ripple comes at the expense of the wider transition region, but this, however, this can be compensated for the increasing the length of the filter. So go on length of the filter. After that, go on using the main lobe. If the main lobe increases, that what you call M values will be decreases. That it will not be affect the problem. Okay, like alternative windows with the time domain. Many alternatives have been proposed in place of rectangular window. Use Hamming window, and Blackman window. Window functions as if it is M is, you can use that M value is different. Yeah, we can constant, if M is constant, if it is specified 10 or 15 or 16 or whatever it is, the time of it is varies. Like in a window function is constant, the time what the effect with the Hamming and Blackman. It is, we'll verify it by using the MATLAB, using the built-in or inbuilt functions. Okay, sample number versus what is the window response with the M values constant or increasing or decreasing. How it is the effect if it is using the time domain. The window magnitude of frequency response. Here, Fourier transform of the windows M is equal to 16. The time. Okay, we will expect the magnitude of frequency response is like this. Here it is. This all are what you call Hamming window. It is specified that all Hamming. Okay, this is a response of Hamming, and what you call and remaining all are okay Hamming and Blackman. Okay, and this is the windows magnitude, different window without this what you call rectangular window. Other than this Hamming and Blackman, what you call windows. Okay, so now summary of the windows characteristics. So the window name rectangular window already we have seen, we have verified, where main lobes are 4 pi by m, main lobe or side lobes minus 13 decibel, and peak 20 log base 10 into delta minus 21 decibels. Similarly, Hamming 8 pi by m and minus 32 decibel, main lobe, side lobe, peak 20 log base 10 into 44 decibel, and Hamming and Blackman windows. These are the major characteristics that we can decide which one is suitable for our optimum or number of errors will be reduced. Okay, you see that clearly that the wider transition region, wider main lobe is compensated with much lower side lobes and thus less ripple. Okay, based on this concept, we can choose either rectangular window or Hamming Blackman windows. Okay, so FIR with windowing techniques. So these are the content windowing method to design FIR filter. FIR filters, it is based on. So we know that if we have made it is this for this digital signal processing course. So we might have had a few moments where we would have thought of jumping out the windows. Already we have seen that what we call rectangular, Hamming and Blackman windows. But bear with me and leave this windowing technique to finite impulse response, non-recursive filters. Okay, trust me, it is not as complicated as it seems. Okay, so introduction to the windowing methods. It would see So straightforward to think that to obtain causal finite impulse response digital filters, we can just truncate the infinite Fourier series of the non-causal infinite impulse response filter. However, in practice, in the practical purpose or in real-time purpose, the abrupt nature of the truncation causes oscillations to show upon the passband and stopband of the filter response. Okay, this based on this frequency response. So this is also known as Gibbs phenomenon that we had previously discussed. We have seen the previous courses. Okay, so the windowing technique in which the windowing function is multiplied with desired frequency response. Okay, so helps this minimize the effect of these oscillations, giving us to more desirable output from the truncation of the recursive filter, that is IAR filter. Okay, this is the relevant to this basic fundamental related windowing method while we are using this interlink with this IAR and FIR, IAR and FIR digital filters. Okay, yeah, but how do you determine the frequency range to ensure you design an effective filter? This is where the windowing technique comes in. Visualize sending an infinite function into a window to get back a finite part of it that enables us to analyze it with more easy. So that is essential what we are trying to achieve with the windowing method. Okay, so with this, breaking things down, first we have to choose a proper frequency selective IAR filter. Okay, after that, this filter usually has non-causal, has both negative and positive points, and infinite duration impulse response. Okay, with this specification of the frequency response is usually uh, given in the form of what you call here is the waveform of the frequency response. The response is in terms of this. Okay, so this frequency response should be converted to unit sample response using the Fourier transform relation. You know that. So we have what you call shown that this is the SD of n versus n. This is the frequency response should be converted into unit sample response using Fourier transform relation. Okay, with this graph of the infinite function. Okay, so SD of omega is equal to summation n is equal to 0 to infinity the SD of n into e power j omega n, and SD of n is equal to 1 by 2 pi integral minus pi to plus pi SD, that is d of omega e power j omega n into d omega. And now we want to send this waveform through a window. How it is possible? It is possible. Yeah, it is possible by using that each and every windows that definition are desirable or what you call related formulas user can it will applicable. Basically truncate the waveform so that we obtain the causal and linear phase finite impulse response filter opposite of what we had before, which basically means finite and probably positive. Okay, so the filter is truncated to a particular length. This length is also known as the window length. Okay, it is specified. Let's say it is truncated at the point n. Okay, the point n is specified, which means the finite impulse response non-recursive filter length would be, we know that m is equal to capital M is equal to n plus 1. Okay, let us rectangular window be that is followed by W of n, which is given as, okay, so where W of n is equal to 1, where n is equal to 1, 2, 3 and so on, n minus 1. So that W of n is equal to 0, otherwise this is in terms of that n versus W of n. This is the waveform of W of n now. Okay, now we are combining the two waveforms, how it is varies, how it is appeared, and W of n to the obtained H of n, the unit sample response of the non-recursive filter, that is finite impulse response filter. For n is equal to 0, 1, 2, 3 and so on, n minus 1, 0, otherwise, okay, hence the graph of H of omega would look like this, which is basically the convolution of W of n. Now we are combining these two waveforms, W of n to obtain H of n. We will expect the unit sample response of the FIR filter like this. So it can be response after the beginning of the filter like this, n versus SD of n. Okay. Now for a bit of perspective, let us take the equation of the linear phase finite impulse response filter, where the order m is even. Okay, if it is odd, m is odd, we will interpret this thing. But this case, FIR filter where the order of capital M is even. Where the real magnitude function we will observe, we are going to start off by minimizing the mean square error between the actual filter and the desired filter. There is a desirability. Based on the desirability, we are going to start off by minimizing the mean square error between the actual filter and the desired filter. Okay, the coefficients of the actual filter is represented by H of k. But normally by using the IARE filter, the coefficients are already calculated, AK and BK. But this case, while you are entering a non-recursive filter, so the coefficients of the actual filter is represented by H of k. Okay, so where represents the desired response and the represent the actual response. Okay, so using this the FIR filter order m is even, we can write that h at e power j omega is equal to the summation k equal to 0 to m h of k e power minus j k is equal to e power minus j omega m by 2 into a omega. Within this, if it is the minimum value hk, the coefficients, so the coefficients of the actual filter is represented by h of k, so 1 by 2 pi integral minus pi to plus pi desirable frequency, that is d power j omega minus h e power j omega square into d omega. Okay, so for a bit of perspective, let us take the equation of the linear phase FIR filter. The order m is even, order is specified where m is even, h on d power j omega is equal to the summation k equal to 0 to m h of k e power minus j k omega. It is also equal to e power minus j omega m by 2 into a power, where a omega is the real magnitude duration. We know that we are going to start that off by minimizing the mean square error between the actual filter and desirable filter. After that, the coefficients of the actual filter is represented h of k like this represent the desired frequency or represent the actual frequency response. The desired filter is also a linear phase FIR filter or not, with the sample group delay or phase delay and so on. Right to represent. Okay, the desired filter is also linear phase FIR filter. The same group delay, let this equation be represented where the mean square error is represented by this value. Okay, so here we require certain what you call Parseval's theorem. See the properties. Already we know that we have seen that properties of DFT, discrete Fourier transform, state that the integral of the magnitude squared in the frequency domain is equal to the sum of the magnitude square in the time domain. Hence that this particular equation, this reflected equation 1. Okay, so what it is squared the time domain, hence the equation can also be written as equation 2, where ak is the non-zero interval minus m by 2 less than or equal to k less than or equal to m by 2. It is the major role in that m value, like minus m by 2 less than or equal to k less than or equal to m by 2, like this. Expand this second equation, right? We are right to verify that the actual equivalent relation with the windowing function. Here the graphical representation, the convolution happening in the mathematical notation. This is the discrete Fourier transform of AD of k, which is AD of omega. Okay, that omega versus AD of omega. This is the magnitude function of desired filter. Okay, the rectangular window function is shown. This is the rectangular window function is the magnitude function of the desired filter. Yeah, the rectangular window function is shown here. K versus W of k, graph of windowing function, m by 2 minus m by 2 plus m by 2. So taking the discrete Fourier transform of the windowing function, we get the graph of the W of e power j omega. Like this, the graph of dt of t of w of k function. Okay, so like this it will specify the based on this graph by main lobe having width of what you call 4 pi by this value. This is the main lobe width. This is all main lobe, no? Here it is. Here. This is the main lobe width 4 pi by m plus 1. The first peak side of the lobes are side lobe of the lobes doing that down to minus 30 decibels related to the main lobe. So the convolution of the window function and the desired filter magnitude response will give us the graph as shown here. So as you see this from the graph, there are many isolations. And ripples represented in stop band and the pass band. The main lobe of the length is W into e power j omega, determines the transition band. Okay, and width of the side lobes determine the pass band and the stop band ripples. Okay, like this, we have to verify that what you call graph of the magnitude with the help of this, the main lobe of the graph of W into e power j omega determines the transition band, and the width of the side lobes determine the pass band and stop band ripples. As you can see from this graph, there are many isolations and ripples present in the stop band and the pass band. The main lobe of the graph of that determines the transition band and the bandwidth, and the width of the side lobes determine the pass band and stop band ripples. Easily you can justify that how it is varies and so on. Yeah, these ripples are not acceptable for the filter of the quality. So quality filter, we will expect the term quality of the filter. I assume this all the main lobe of the graph of determine the transition bandwidth, and the width of the side lobe determine the pass band and stop band ripples. Okay, with this, too many ripples on the pass band and stop band will not let filter do its function that you call well enough. Okay, so typically other windows are used to treat the main lobe width or transition band or the side lobe width ripples. If the transition band, main lobe or the side lobe width are ripples, how it is increase or decrease based on that main lobes and side lobes, or maybe what you call In terms of transition band or maybe ripples, we will decide the factor, the filter of the quality. Okay. With this, yeah, these are the types of windows. Rectangular window, that window function is W of n is equal to 1. The shape of the window function like this, width of the lobes of the frequency responses, main lobe, width, and so on. Okay, like this Hamming and Hanning and Blockman and Kaiser. These are the expected waveforms. Okay.
Like, share and subscribe. Hit the bell icon for more updates.